Let's move on to power management. I'll say that some of this material was covered by Shannon yesterday, but I'll give my perspective on it. A lot of this content comes from when I was advising the Walnut Solar Car team circa 2015 to 2017, and I'll have my real data, and then you looked at Shannon's real data from his Covenant team yesterday, and you can sort of take a look at these data points and consider how these might apply to your team. So what's the importance of power management? It's really looking at how much power do you need to get on the road, and what those considerations are. In part of your design, your aerodynamic drag, your rolling friction, your weight, your electrical system resistance are going to be key parts of determining how much power you end up using in your car. Well, in addition to that, you heard yesterday from Shannon that driver skill and driver style is a critical part. You'll know that if you accelerate an electric car quickly, you don't get a linear graph of how much energy that you use. It's really exponential. So you really want drivers who could slowly get your car up to speed, and then to take advantage and like coast and cruise down in order to really get the most out of your power. So how much power do you have, right? So that's really based on your solar array. A typical solar array in terms of the classic division, I'm not counting advanced division car, you're talking about 800 to 1,000 watts as a rating, right? That's how much your array is rated for. You take that over to 12 hours of sunlight, you would say, oh yeah, I've got about 9,600 watt hours of energy. That's not really what you got, right? You got to consider the time of day and the angle of the sun. You got to consider clouds. You got to consider all those type of considerations. And so you don't really have 9,600 watt hours to use in the course of a day. And then you apply that to your battery pack. Let's say you have 4,000 watt hours, like in my previous example, for your battery selection. Well, because of the battery chemistry and how things charge, you really can't just put 4,000 watt hours energy in order to get a fully charged battery. And when you get to the very end of your charging cycle, it takes a lot more energy to force your energy into your battery. So it might actually take something closer to 5,000 watt hours to fully charge a 4,000 watt hour battery pack. So lots of considerations there in terms of you've got all these theoretical data sheet ideal situations, and then you've got reality. And so you got to look at that reality. So let's take a look at what that reality looks like. Okay, first off, how do I determine the sizing of my batteries? Dead batteries are dead weight. So if you can't charge up your battery and they're just not usable, you're just carrying weight without any benefit, right? And so you got to look and say, based off of my battery pack, can I fully charge my battery so that they're usable over the course of the 4 days on the track, or if you're talking about a road race, the full road race? And then you got to consider, even if I could calculate the ideal situation of how much time it takes to fully charge my battery, what about all the other environmental conditions? You know, if I have hills, I might end up having to use more energy than I expected. If I have clouds or trees, I might have, less energy coming in. If I have children with sticky fingers, you might start losing some of your array efficiency because you've got some residue on your array. And as I was talking about, if you have a full array and they're all wired in series, any one cell that is working less optimally affects the entire string of solar cells. So take an experiment. Go out and get your solar array, wire it up to a load, get a multimeter on it, and measure how much current do you get from the sun, and then cover one cell fully. Measure how much current you get. It'll basically be near zero. Cover half of it. You'll probably get half of the fully rated power for the entire module, even though you only covered one cell or half of one cell. So it's something that you need to keep an eye on. So the only way to really know practically how much energy you have coming in is to test your car, right? Go and start collecting information on it and keep a record of both your inputs, like over the course of the day, how much current do you get coming into your solar array and into your batteries. And then likewise, go test your car in terms of the output side, right? How much energy am I going to take to run my car at 15 miles per hour, to run at 20 miles per hour, to run it at 25 miles per hour? That is not a linear graph, right? So you have to look and see where that fits in. It's generally exponential. Okay, so I never try to tell teams what the optimal solution is. First off, it's an engineering project. There is no optimal solutions. There's always trade-offs. And it's the trade-offs that you have to make in terms of what your strategy is. So when you think about high-level strategies, what are some of your options? You could choose to say, I'm planning to empty my battery pack each day and then recharge to some level not full, right, during the off hours. And then I would essentially have less energy to use at the beginning of the day. You could calculate and say, well, by the end of the day, I can only have, I can only be, let's say, 70% down on my battery because given the amount of time that I have left to charge at the end of the day and the beginning of the next day, I can't fully discharge your battery pack. So if I wanted full batteries at the beginning of each day, then I can't use up all of it. Or do you say, well, I've got a 4-day track race, so maybe I could not be fully charged at the beginning or at the end of each day. Maybe I'll just go, a quarter of the way, and by the end of the 4-day event, I'm completely dead, right? So there's no correct answer here. This is just something that you consider in terms of your strategy. Next thing is, do you do all those calculations based off of the net draw or based off of the motor draw, right? So the motor draw is basically how much you're driving in the solar car and using up. But that motor draw will draw from both your array and your batteries. So if I calculate this, let's say if I run my car based on net draw, if I have fuller sun, I'll be running faster. And then if I have lesser sun, because I have less array voltage or array power coming in, I'll be running slower. I'll have a variable speed, running down on the track. Whereas if I calculate just on more consistent motor draw, then I'll be running more consistent speeds. That might sound like I am veering you towards like a motor draw strategy. I'm not. I'm just saying you need to consider, hey, do I want to go through the complexity of calculating more constant motor draw and having to adjust things, or do I let the vehicle drift in speed up and down based off of the sun? It's just a strategic decision, and it's based off of how much effort you want to do in controlling your car and the driver and how much output that you use. Okay, so once you've set your strategy, then you start doing the calculations, right? So let's talk through this thought experiment. If my strategy is to end the battery, end the day each day with an empty battery pack, and I have a 100 amp hour battery pack, how fast should the driver drive? Any answers? If I've got a 100 amp hour battery pack, I've got let's call it a 6-hour driving day, how fast should the driver drive? It depends on the amp draw of the motor. I can't determine that. And nobody can determine that in terms of the strategy team without relevant data can't tell you, hey, go 15 miles per hour, go 20 miles per hour. It's really based on your current draw, right? It's not based on speed. Now, there's a correlation, and if you've got the test data, you're able to do that correlation, right? So, okay, now let's talk about, okay, yeah, it's current draw. Well, how do you calculate that, right? How much current should you be taking from the battery? Well, you got 100 amp hours over 6 hours of racing in the classic division, so I should drive at 16.7 amps, right, net draw. Is that right? And then, of course, you've got Pucher's equation, so you start losing some of that efficiency. But you have to consider that our classic division cars and electric solar and basically non-advanced and non-cruiser cars run in a 3-hour running time, 2 hours of rest time, and then 3 hours of running time, right? So really, I have to consider how much charge do I get back during the lunch hour when I can charge my batteries. And so ultimately, rather than 16.7 amps, you could, if you drove 16.7 amps and then you wanted to empty out your batteries by the end of the day, you're saying, in the morning, I'm going to run 16.7 amps, and then, oh, wait, I forgot to consider the charging from the lunch period, so now I'm going to drive 30 amps on the afternoon session. And so that's non-consistent, right? So essentially, in order to do the same current draw throughout the course of the day, you would be really driving 23.3 amps. So these are some of the considerations and calculations that you'll want to have when you get into the strategy mode of the race prep. So you couldn't do any of that without the ability to collect that data. And so you want to at least be able to get your volts and your amps coming in. And so you could simply take an analog voltmeter and ammeter and just start radioing back answers to your control tent. And you can do that way. I've seen teams do that, and it's worked. You could have other displays that'll give you a little bit more information, including this Batman design or this Link 10. And some of these systems allow you to actually get the data out via a CAN bus or via serial connections or things like that. And then you could create a telemetry system that sends the data back automatically. In our teams, we use the Link 10 design, getting it out a serial port, collecting that data via a Raspberry Pi, and then sending that up to the cloud, and then we would, in our control tent, collect that data and perform the calculations and give us the ideal driving target. If you don't have that level of complexity, simply radioing that back from the driver and putting that in a spreadsheet is just fine too. But any way you can, get that data back so that you could use that information to determine how you execute your strategy. So what data is important? We already talked about battery voltage. Your motor and array current would be important. And then if you have the ability to track the state of charge of your batteries, that would be ideal. And some of these battery management systems, if you're using lithium iron phosphate, does provide for that tracking. The Link 10 meter does estimate the state of charge of lead acid batteries as well. So that really gives you some backup to all your battery voltage and current draw calculations. So I'm showing you now the data from our race in 2017 on a particular day, July 21st, 2017. This is the electric solar division. What you'll see here is we calculate watts, essentially the power that we are expending, the main battery current that we're expending out of the batteries, and then the main battery voltage that we're using. What's interesting about this data? Some thoughts. The pole? Oh yeah, the pulses. Yeah, you know, you get some holes in the data that's right there, right? What else? Right, you see things that advance up and then it pulse and then you start over again. Why is this interesting? I didn't tell you the full story of this graph. This graph represents the charging characteristics of an electric solar division car. So what this is in the electric solar power division, you have a set of batteries that are in your car that discharges. And then you have a set of batteries that are on your charging station that charges. What you see in terms of the pulses is the interval between the charging sessions. Every dip in the graph where it zeroes out is when we were swapping batteries between one battery pack and another. And so you'll see that as the batteries get charged up to near full, that's likely also when our battery pack in our car is empty. And so we bring the car out, we do a battery swap, and you'll see the state of charge of the new battery pack that we put in is lower, and then we got to charge it back up again, right? So this data really tells us how long does it take to charge a battery, right? How much current am I getting in over the course of the day? Look at this. The variation of the morning charging session versus the afternoon charging session is significantly different. That could be a weather phenomenon, and you can see that drop right there as well. That could just be clouds and things like that. It could be, we weren't optimizing in terms of the angle. Could be all sorts of considerations there, right? So this is another piece of data that we collected, and this is the difference between speed and current draw, right? So speed is the vertical axis, current draw, we mount it as negative, meaning we're pulling current out of batteries. And so I drew this sort of line to say, try to fit in the data. But I'll say that as you saw yesterday in Shannon's graph, that line's not really a line, right? I mean, you really have more of a curve to it in terms of your speed versus current trade-off. And then, based off of your acceleration, you may have some outliers. Look at this, right? I mean, we're looking at 25 miles per hour, and we're drawing somewhere close to like 90 amps. And that's likely more of, the driver really pushing the acceleration to get to that level more than it is, the normal cruising speed. So, you want to collect this type of data to help you be able to use that data in your decision making. So how do you get that data? You need to, this is why we encourage you to have testing periods. You heard us beat that into you all throughout this workshop, is leave time to test. There's no way we could characterize our vehicle being here at the Texas Motor Speedway. When I was part of our team in Walnut Solar Car, we were working in a shop that had a straight road that was like an industrial area. So when we worked on the weekends, it was abandoned, and it was fairly flat, though we had a little bit uphill on one way, a little bit downhill in the other way. But we would just make runs back and forth. Every run, we would be collecting data and saying, for this speed, this is my current. For this speed, this is my current. And we used cruise control. So we took the driver acceleration out of the question here, and we just characterized that over and over. And then that really got us the data we need to be able to decide, what is my gearing? How far can I go on a particular charge? What's the current I can do? We even went to the point of, once we characterized our car, to say, let's run a simulated race day. Let's plan a really long day and say, hey, we're going to start the day as if we were going to pull the car out of impound. We would charge it up in the morning. At 9 o'clock, we would start running up and down the road until 12 o'clock. Take the lunch break, charge our cars, and then run 2 to 5 and run up and down the road, and collect the data. And that helps us get the data that we need for a given day, get some practical information, and it also trains our team to know how to handle a particular day. We simulate the radios, we simulate our decision making, we simulate driver changes. All that is part of that simulated race day. So how do you make decisions? We always say that even though, driving is fun and driving is cool, the driver is probably the least important person in terms of your how you run a race. Yes, they're really important to ensure that they can drive safely and that they don't crash into other people, but the driver is essentially just a robot, right? The driver does not get to determine, I'm going to go 25 miles an hour right now. Your strategy team is the one who's going to say, hey, drive at 20 amps right now. Drive at 25 amps right now. Drive at 30 amps right now. The driver just needs to listen to that. And of course, if you got telemetry coming back on a regular basis, your strategy team might even be yelling at the driver like, hey, you're accelerating too fast. Be smoother, things like that. I remember one time that we built an experimental vehicle just to demonstrate some capability, and I, due to some lack of sleep situation, wasn't allowed to drive the car on the track, and I basically had to get Jarrett to help me drive the car, and I essentially, just like the strategy team, say, hey, drive at, I think I said 30 amps or something like that. And so he goes out there and drives around the track, and it's been, 10 minutes and I haven't seen him. It's been 15 minutes, I haven't seen him. I'm like, what the heck is going on here? He's like putting around. All the teams are like passing by him. I think he's going at walking pace almost. And what happened was, in my instrumentation, I had a 0 to 500 piece of paper for the amps draw, but really the ammeter was wired with a 0 to 50, shunt. And so ultimately, even though I told him to go 30 and eventually 40 and 50 amps, which is like fairly fast, he was essentially going 3 amps, 4 amps, 5 amps. He was actually telling me that I'm charging while I'm driving around the track. So some of the things, it's a little bit about power management, a little bit about your electrical system. Just make sure that everyone knows how your instrumentation is and how you use that data. We also say that you should talk about speeding up and slowing down. As you collect data, as you sort of make live changes based off the environmental data from the array, based off how the driver operates, you might end up having to do some real-time changes in strategy. And so the pit crew is really the one that decides that, right? And then it's more of a operational thing, but a lot of times we see teams, every team member has a radio on them, but we've seen successful teams have like a separate radio or have enough radio hygiene that says, hey, have one person talk to the driver so that he doesn't get inundated with different requests. Like if you've got one person that says, speed up, another person that says, slow down, another spotter that says, hey, there's a car coming around you, the driver's just gonna go crazy, right? So you wanna have that pattern of having one person go and communicate with the driver at a time. And then your telemetry systems can be used not only to collect input data, but to determine optimal output. So what we did is we have some computer science oriented students on our team. So they actually went and instead of getting just the data and then looking at it and analyzing it, they actually wrote programs to be able to analyze the data and give us the optimal current draw or the optimal speed that we want to be running at to get to our strategy. So if you have people on your team that are more programming oriented and you have that telemetry data, this is a great project for you. We talked a bit about this, but I'll just reinforce, once you have all that data, then you could use that information to decide your gear ratio. Some of the other considerations in terms of your strategy, you got to consider weather, and you might have to make real-time adjustments to your strategy based on cloud cover and weather predictions. And so one of the things that we do is to look at the weather forecast for the day, cloud cover over the course of the day, and then make changes based off that. You got to look at how much power that you get at different angles of the sun. You saw Shannon did that very scientifically by going out and looking at what's the global horizontal radiation for that particular location at a particular time of day. You got to look at different array shapes, right? If you have not a flat array, but you have angles to your array, how does that affect the power that you get coming in? If you wire a left and the right side of your car, and they're at different angles, if you wire them in series, you're going to get the least performant of whichever side it is, not the most performant. And then if you're talking about on the road or if you're talking about track layout, how does that affect things, right? If we're on a road race, if you're headed west or if you're headed north, that may change your considerations. So, this is the fun part of the race, right, is to be able to, once I put a car together, how do I make it run most optimally so I can get the most out of my car? So I think that's pretty much all I have. Anyone have any questions on power management?